Hello, everyone. My name is Mitch Savali. I'm currently enrolled in Physics 2211, and this is my lab report on our first lab, which is constant velocity. Just a quick overview on what this lab is going to be about. Mostly, we deal with Newton's second law and the momentum principle. I'm going to explain more about that later. But what we do is we are electronically tracking some data and using a computational model to compare it to the actual results. And at the end, we're just going to be concluding with some questions and just overview of all our results. So to start out, the purpose of this lab is to visually demonstrate the properties of Newton's second law, also known as a momentum principle, and to compare the experimental data to a computational model of the expected motion. Just a couple of important equations that we're going to be needing related to Newton's second law. The first is final momentum equals initial momentum plus F net times delta t. This formula tells us that a system with no net force acting on it will have no change in momentum. And then similarly, we can derive an equation for velocity, which tells us that the final velocity equals the initial velocity plus F net over m times delta t. This shows that velocity will also be constant in a system with no net force acting on it. And in this experiment, the system is the ball and the surroundings are everything else. Just the process for this experiment is to start, you're going to record a video of a ball rolling across the floor, and you're going to upload it to a tracking software, which will have a frame-by-frame analysis of the ball's position and time, which we will use that data as our observed position. Next, we're going to develop code to match the initial conditions of our velocity and position, and that code will predict the motion of the ball, and we can compare that to the observed position graphically. So over here on the left is the video of the ball rolling. It's rolling to the left, and at each little number there, that's the frame-by-frame analysis of the ball. So you have each frame has new position of the ball, and on the right here, we can see that graphically, where you have time on the bottom and time on the x-axis and position on the y-axis. And in this, we can see that the ball is moving to the left. Therefore, it has a downward sloping line with a negative velocity. And it's pretty linear, the line, because the ball had a fairly constant motion, a constant velocity. So important values that we're going to need for our computational model is the total time the video lasted, which was 0.511 seconds, the initial position of the ball, which was 0 meters, and the initial velocity, which was negative 1.31 meters per second. Keep in mind, it is negative because the ball was moving to the left. Here we have our computational model, and so what we need to do is plug in those values from earlier. As you can see first, we had to input the initial velocity and position of 0, 0, 0, and a velocity of negative 1.31 in the x direction. Then we had to make adjustments to our time and position equation. So for our delta t, we had to make the adjustments based on the frames, and that was the same with our velocity. So if you see at the bottom, our velocity in the position update equation is negative 0.029, which we did that because the frame rate was 45 frames per second, and you have to divide the velocity by the frame rate for the computational model to run correctly. Here we have the graph comparing the observed data with predicted data, time on the x-axis, position on the y. As you can see, the predicted data is a perfect linear line. However, the observed data isn't quite perfect. It's fairly linear, yet there are some forces acting on the ball, like wind resistance and friction, which cause it to have a slightly changing velocity. And just to conclude some things, some possible errors that could have occurred in this experiment is the ball not rolling completely straight, therefore the tracker having an inaccurate result of the ball's position. And then another error that could have occurred is some rounding errors that we made when doing calculations. Just a couple questions we can ask about this experiment is, what if the axis were flipped? Then the graph would have a positive slope. You can see that on the right with a positive linear slope. That would also occur if we roll the ball to the right instead of to the left. And just overall, from our results, what our results mean from this experiment is our predicted motion tells us what happens when the net force equals zero. And in this experiment, the net force is zero because the normal force, which is pushing upwards on the ball, is equal to the gravitational force, which is pulling downwards on the ball. Thank you for listening to my lab report, and have a good day.